seminar, I thought the best thing to do really would be to give you something that would be a little bit more accessible to you than the research that I do, because I feel this would possibly be, you'll be able to connect with it a little bit more. What I'm going to show you is really 3 projects that our final year undergraduates have done, and they've been pushed on forward a little bit by myself and another member of staff. I mean, my actual research interests are those. The first 2 are fairly chewy. So the third one, engineering education, I'm really interested in, but I really haven't been going on it long enough to really give you anything that you don't already know, probably. So that's why we're talking about these undergraduate projects. What I want to do is, just in case you don't know what a thermocouple is, explain what a thermocouple is and how it works. I will then talk about my second favourite equation, because it comes in. I'll short circuit the questions. My favourite equation is Newton's second law. Okay, that's because my degree is based on that. No Newton's second law, there'd be no mechanical engineering. So, but anyway, my second favourite equation is the lump capacitance model, and I'm going to talk about that here because that really brings in most of the analysis that I'm going to look at when it comes to looking at heat fluxes and looking at flame flicker. When I say cheap fire detection, well, I mean cheap fire detection, I'll talk about that a bit later on, but I'm also interested in intelligent fire detection. So rather than just there's a fire, there's no fire, I'm looking for something that will give you a bit more information. So it will tell you where the fire is, it will tell you how the fire has grown over time, and you can imagine that that data goes into a little black box and then maybe is used in fire investigation after the fact. That's the idea. Okay, and then we'll finish in the usual way. Conclusions and future. Thermocouples are incredibly simple things. They're really just 2 pieces of metal joined together at one end, called the junction or the bead. And Seebeck, Mr. Seebeck or Professor Seebeck, I'm not sure which, he discovered the effect that's named after him, where if you heat up the bead, what you get is a temperature difference across in the circuit. And depending on what those materials are and the range of temperatures you're looking at, you get a fairly linear relationship, so you can measure temperature in that way. Depending on what you want to measure, you get very cheap thermocouples or you get very expensive thermocouples. In fires, most of the time we're using type K thermocouples. This is a sort of a nickel alloy, chromium and aluminium. And they cost around $8 New Zealand. If you want to measure a higher temperature than 1350 degrees C, so you're looking at something like a jet fire, then you're going to need something other than type K, and the platinum cranks the price up quite significantly in the sense of you're looking at, I don't know what you get, I'm doing the pound conversion. In the UK and New Zealand it will be about $400 or so. So I'm talking about type K thermocouples because it's cheap. I'm a computational modeler. I need experimental data. That's where I'm coming from. Computational modelers, by and large, are poor people because they've only got a PC. All they need is a PC and a room, and that's it. But they need validation data as well. Okay. Lump capacitance model, just in case you've never come across that before. I always show this slide to my first year, and they like this slide. Imagine you've got a lump of steel come out of a furnace, dump it on the ground, and it's going to lose heat by convection to the surroundings. Temperature is going to drop in that sort of way. What they don't like, my students, is that equation, which is the lump capacitance model. They're confused by it by and large because of all the different parameters in there, but most of them are constants. You've got the mass, you've got the specific heat capacity, heat transfer coefficient, area, ambient temperature. If you put in most of the values that you know in that, then you end up with something that's far more simple, which they're not afraid of, whereas the other one they probably are. You're going to see that crop up a few times. Okay, this is my second favourite equation because it's so useful. Okay, people use it for measuring heat transfer coefficients. In safety, it's used to model rollover, which I won't go into now. You can use it for as a self-heating model with a bit of a change to it. You can also argue that a fire zone model is a lump capacitance model, because essentially the only real assumption in the model is that your lump has a single temperature. Okay, so what I'm going to look at is this. I'm going to see how we can measure heat fluxes and velocities, and as I say, we'll look at flame flicker as well. When it comes to measuring heat fluxes, if you're going to use conventional ways of doing that, then typically the sensors are quite expensive. The ones that you've got here are about $800 a bang. They're water cooled, so you can use them in the lab, but you cannot use them in the field, unless you have a river nearby maybe, I don't know. And often they can be quite limited in the spectral range that they'll actually measure the heat flux over. So 1 to 6.5 microns, 1 to 10 microns, depends on the window on the heat flux gauge. Whereas, I mean, that's where most of the energy is, but I mean, the thermal radiation is over a much wider spectral window. So ideally, I want a heat flux gauge that's going to give me that. This idea of using thermocouples for this is, it's not a new idea by any means. I would say it's a useful thing though, so it keeps reappearing with different contexts to it. The first that I'm aware of is in 1998 when some of these two guys were looking at doing a storage rack experiment. They wanted heat fluxes all over the place, and so they formulated the heat flux model for this particular context, and they had about 40 heat flux gauges, or 40 thermocouples rather. So they wouldn't have been able to instrument it out in that way with normal heat flux gauges. Their model, or the heat flux model they use, as you've got it up there, that's the thickness of the little piece of metal that they attach their thermocouple to. And what they were measuring was the total heat flux. It's only really useful in the early stage of the experiment though, because as time moves on, the temperature sort of looks like that. And where it's steady state, all that's really telling you is all of the heat or the energy that's arriving is leaving, so it isn't telling you anything. So it's only in the early stages you can really use that. Ingerson took this one stage further, where he took a flat plate, welded a thermocouple to it, and used it to measure heat fluxes in furnaces. Quite slow response because of the size of the flat plate, and it required calibration. So you needed a heat flux gauge to produce a heat flux gauge. It's no good to me. So I and a student of mine, Joanna Murray, came up with this idea where we were looking at radiation fields, and that's what I'm going to talk about, external radiation fields to jet fires. That's what I'm going to look at. Since then, another bunch in India have come up with much the same idea, looking at internal combustion engines. So as I say, it's not clever, but it's useful. This is my configuration. You've got a jet fire, basically a large-scale Bunsen burner. I've got a thin, flat plate of steel, and underneath I've got some polystyrene to give it some insulation. Makes its analysis a little bit simpler, and I've got my thermocouples all tied into a data logger. And then if I run the experiment, this is the sort of thing I'll get where the temperature's heating up, there's all the different thermocouples, and then if I turn my fire off, then the temperature decays. And we can use that to get the heat flux, but we do it in a sort of a backwards way, in the sense that we look at the cooling down phase first. You can write out the lump capacitance model in this way for the cooling down phase. It's different to what I showed you before. It's got radiation in there, so a net radiation term. Here we've got the background radiation, because it's cooling down, there is no fire. And it's per unit area, so there's no mass here. I've got the density, I've got the thickness of the plate. Okay, and the reason why I'm interested in this is principally because I know it's steel, so I know the density, I know the specific heat capacity, I can measure the thickness of the steel. That's the emissivity, I've measured that previously. So and I certainly can measure the ambient temperature. So the only thing I don't know is the heat transfer coefficient. So what I can do is I can adjust my heat transfer coefficient so that my model can predict the experimental data. When it does, that's the heat transfer coefficient. Okay. We can certainly talk about the validity of this afterwards if you really want to. Happy to do that, but I'm not going to do that now. Now when it comes to heating up, it's basically the same model, but rather than background radiation, we've got some background radiation plus the contribution from the fire. And the only thing I don't know in this model is that during the heat up phase, because the heat transfer coefficient I've already calculated from the cool down phase. Okay, so then I can adjust that so that I can get agreement between the measured and the predicted temperature. These are the best I've got, admittedly. They're not all like this. But you can see that I've adjusted my heat transfer coefficient to get agreement with the measurements. Got a value of about 22, 23. And from that, can then feed that into the heat up model, adjust my incident heat flux, and I get 1.2 kilowatts per meter squared. There we go. The question then is it any good? Certainly it's a very good fit. That would suggest that the model is very good. But we really need some way of validating this. So I'm going to use a model to validate some experimental data, which is almost against the law in engineering terms. When my students say to me, the model validates experimental data, then I usually burn them. If I could, I can't burn them, but verbally I burn them. But it's slightly more complicated than that. I'll run you through it, okay. What we do is, first of all, I've got this jet fire model, been working on it for years, other people have been working on it for years. It's reasonably well validated against a lot of jet fire experimental data. This is one example. This is a natural gas jet fire, Reynolds number of about 6,000. And this is the temperature field. You have to read it from here to here to here. And these are predictions and measurements of the temperature at different axial distances. So about 50, about 100 diameters downstream, and about 150 diameters downstream. So it's pretty good. I can do the same with the major participating species, so the carbon dioxide and the water vapour. I can predict it like that. The intermediate species I'm not very good at, but I sort of don't care here because the carbon monoxide doesn't emit much radiation. Okay. So we've got a decent jet fire model. I've also got a radiation model. It's a narrowband model. It's actually developed by Gross Handler in America. But what I've got here are measurements and predictions of incident heat flux. Okay? What I've got is phase measurements where the spectral window was 1 to 6.5 microns, and I've got my measurements using the thermocouples, which are really taking radiation across the whole spectrum. Okay? I predict phase data, and then I have a go at predicting my data with Gross Handler's model, and it's pretty good. I've got others I could show you, but I have other things I want to talk about. So if you like, the logic is this. I'm using phase measurements to validate this measurement technique. Okay. So it's almost like I'm using a model to say the measurements are good, but not quite. I am actually using some measurements here. I actually got that through a reviewer, or some reviewers, which I was quite pleased about. After the fact, I got my hands on a black body source, and that meant I could actually calculate measured or theoretical heat fluxes to compare against not my technique, but the technique using thermocouples. I did this with a slightly different sensor. It's still a thermocouple, but rather than a steel plate, I'm using a piece of tin foil painted black, measured the emissivity. Okay, with a big chunk of polystyrene to give you the insulation. Those dashed lines are at 15% difference to the identity line. There are errors in the experimental data, and there are some assumptions that are required to calculate a heat flux from the black body. So, that's why we have some scatter in that data, but by and large, I'm happy with that. Okay. So that is heat fluxes. It's a fairly conventional way of measuring heat fluxes. $4 rather than $800. Velocity is a little bit more interesting, I think. The basic idea is this. You have two thermocouples, and you have a turbulent eddy. And providing those thermocouples are close together, as the turbulent eddy passes through the thermocouples, the two temperatures that are measured should be similar in some way or other. They should be correlated. Okay. If the turbulent eddy is very small, then the fact that one is going up while the other one is going down or whatever, they won't be correlated. The correlation will be just destroyed by the sort of the turbulent, chaotic nature of the fluid. But if they're close enough, they will. I mean, this is highly idealised, but essentially, you'll get a signal out of it. We're interested not in the temperature. I use the voltage because it's a bit quicker. I can log more quickly with the voltage. Then, ideally, if I see something like this, that would be absolutely brilliant, because all I would have to say is, okay, well, the signal starts here on the lower thermocouple, the signal starts here on the upper thermocouple, then I know the distance between the two, I can get the velocity out of that. That's the idea. Now, there's a few issues here. One, I'm probably going to have to log very, very quickly. That distance, delta, is going to have to be chosen quite carefully. These thermocouples are going to have to be really quite small because of the thermal inertia. If they're too large, then they respond slowly. And so you cannot capture something that is moving quickly, if you see what I mean, in terms of temperature space. And the other thing about this, of course, is I'm very unlikely to see a signal like this where I could look at it and say, okay, that's the phase between these two signals. It's not going to look like that. So we've got a few issues that have to be resolved. Maybe they can, maybe they can't. The student designed this rig to investigate this, and what you've really got is you've got two lots of thermocouples, first of all, what are called the voltage thermocouples, because all we're doing is measuring the voltage. They're the ones that are going to be seeing if we can measure the velocity. Okay? And then inside this box that's insulated, we've got a heat source and a chunk of metal, some insulation. The whole idea is so that we get one-dimensional heat transfer through here, and we've got thermocouples here. You could use those thermocouples to measure the heat flow, which is what I would have done, but anyway, the student chose not to do that. What the student chose to do was actually to use those temperature measurements to infer the surface temperature, extrapolate the surface temperature. Okay. I think I've got a photo of the rig here. The chimney is there to sort of like, how can I say this, to sort of amplify the velocity in some regards. That's the best way to describe it. I've got a few of them. Let's just go through these. So we've got our box. The middle bit is the heat source, or the metal where the heat is coming out of. And then polystyrene balls to give us the insulation. I'm afraid I cannot remember the diameter of the thermocouple. But it's very, very small. No. And there's the last one of the chimney. Okay, so you get the idea. If we're heating air up here, it's going to go through here and then advec past the two thermocouples. These are the sorts of signals that you get. This is logging at 1700 Hertz, so we're logging very, very, very quickly. Certainly, if you look at those two signals, you couldn't say anything about whether they were correlated or not correlated, or where the phase is. You've really got to go to some signal processing software on this. And if you do that, you get a number of different things out. These different experiments are delineated by the temperature on the surface of the heater. Okay, so this is the hottest one we've got. And what we've got here is a Fourier transform of the time series. We've got two Fourier transforms here, actually the lower thermocouple and the red one is the higher thermocouple. You've got amplitude versus frequency. I'm not a signal processor by any means. I just think of these in terms of you're representing that time series, a whole load of cosine functions that have amplitudes and wave numbers in there, or frequencies in there. Really, this is here to show us that the two time series, although they look, I was going to say chaotic, I suppose they are chaotic, they're turbulent, they're really giving you very similar Fourier transforms. What that is all about is actually an anomaly. That's at 50 Hertz, so the thermocouples are picking up on the power supply. Okay, at 50 Hertz, AC power supply. I'm not sure what these are all about. It's been suggested to me that they're to do with the thermocouple leads acting like aerials, but I don't know. Okay. But now if we move on, we've got two graphs here. They're really convolutions of the two time series, and the two things we're looking at are coherence and phase. Okay? With coherence, what we're looking for is a non-zero coherence that is not all over the place, if you like. Here it's going crazy at the higher amplitude, higher frequencies, I beg your pardon. So we're interested in this part of the data. And the phase, which is what we're going to get the velocity out, we're looking at a nice linear phase frequency relationship, which is what we need. If it looked like this everywhere, we wouldn't really be able to do anything. What it would mean is our thermocouples, thermal inertia is too much, or we're not logging quickly enough. Essentially, we wouldn't get something that made sense. So we take the phase and we a straight line to it, and the gradient, we can get the frequency versus phase out of that, and then we can calculate the airspeed if we know the distance between the two thermocouples. So in these particular cases, 3 millimeters. There was a bit of experimentation done to find that optimum value in this particular context. In many regards, this, I mean, you don't need thermocouples to measure velocity. There's lots of other ways of measuring velocity. This is sort of like an application, sort of a technique chasing an application, if you like. Hasn't got an application. If it had one, it's idle curiosity. If it had an application, I'd be far more interested in it. But if you do this for a whole load of different heat flows, so surface temperatures of the heating element, then, and plot it against Rayleigh number, which is, if you're not familiar with that, it's a bit like a Reynolds number. So it's equivalent to a Reynolds number, but for a buoyancy-induced flow. And so we would expect that as the Rayleigh number goes up, we would hope that the velocity goes up, and it certainly does that. The next thing to do, I guess, would be to actually take some other technique, LDA or something like that, and measure the velocity to compare the two. We haven't done that. We haven't got an LDA system we can use. To my mind, we've sort of taken it to proof of concept. I don't think we'll take it any further than that, unless we can come up with some application. If we can come up with an application, then we'll get more interested in it. This is myself and Tycho Donovan. I'm the modeller, he's the experimentalist. Okay, so flame flicker and fire detection. There are lots of different fire detection technologies out there. Smoke, heat, flame detectors, as I've got them up there. I'm particularly interested in the flame detectors. I'm sure they're used in other places as well, but they're used offshore. The oil and gas companies, they have money. That's why I'm interested in them particularly. And these things are very expensive, probably nothing to an oil and gas company, but about $2,000 a bang. I'm sort of hoping that I could do it for $8. Well, yeah, $8. Now that's a real ask, to be honest. I don't think I'll be able to do it for $8. I'll need a little bit more than that. But $20 maybe. Convincing them to take on the technology, if it worked, would be a different matter because they're incredibly conservative people. If you had 10 oil companies and 9 of them spent $2,000 a bang, and the other one would look at it and say, you'd say, okay, I can do it for $8. A, they would never believe you. And B, they would say, okay, well, I could save myself some money here, but I'm far better off doing the wrong thing that everybody else does, and then I won't get into trouble because everybody else does it. So, there's issues here. What I'm sort of doing with a thermocouple is really a combination of the two, because a flame detector is a radiation detector, and I'm using the thermocouple to be a radiation detector. And obviously, it's a heat it's radiative heat transfer I'm interested in, so it's sort of like a heat transfer, heat detector. But it's more like a flame detector than a heat detector, in my opinion, because it has a fast response. Heat detectors are quite slow. The other thing is they don't use heat detectors offshore because of the speed. They don't use smoke detectors offshore because often most of the time they haven't got a ceiling, so they haven't got anywhere for the smoke to accumulate. They don't know where to put the smoke detectors if they were to use them. Okay. Flame detectors are detecting the radiation from the flame, and ignore the wideband prediction. That's a model. This is a methanol burner, methanol furnace, I beg your pardon. It's one of Gross handlers from his PhD. And what we've got is a spectral intensity distribution against wavelength, and for hydrocarbons, the emission is banded. And that is really what flame detectors exploit, because they work on the basis of, they look at the spectrum in up to about 3 places. And for example, CO2 emits strongly at about 4.3 microns. So if I get a lot of activity here, and not very much activity here, that suggests to me I've got a CO2 fire, or a fire that's emitting CO2. These bands down here are a combination of water vapour emitting, and I think there's a bit of carbon dioxide in there as well. So if you can characterise your fire as a hydrocarbon fire, so you can use that information. That's sort of how they work. Well, I'll show you this. I had this in the overheads, but the size went to about 800, about 300 megabytes, so it just got very, very sluggish. So this is a square pool fire, and everybody can see the flicker. I actually focus in pearls of wisdom. Charlie's doing this, I'm sure. At one point I had this video upside down. I was contemplating using it that way because you take a bit more notice of it then, but I didn't anyway. So what I focus in on is here, because you can see the oscillations in the shadow very, very clearly. Whereas I find the fire a bit mesmerising. You can either look at what's going on up here, or you can sort of look at the vortices coming off it. But it's a very strong feature. Very strong feature. For a jet fire, the only difference is that the oscillations, the frequency is much higher. Okay? Okay, when it comes to flame flicker, what you're looking at is something that is running, it will flicker from about 1 Hertz down to 20 Hertz, or up to 20 Hertz, depending on the size of the flame, the fire base, if you like. If it's a jet fire, it will be nearer the 20 Hertz. If it's a pool fire, much more down at the slower end. And this, as I say, it's a very strong feature. You can actually measure it by putting thermocouples inside the flame. It's quite a difficult environment, so you've got to have quite large junctions in there to really see the flicker. So you can only really pick it up at low frequency. But similarly, if you measure the velocity using some laser diagnostic technique, LDA, you can certainly pick up the flicker. Or even put a pressure transducer in. You can pick it up from the pressure field. So it's a very strong feature. Obviously, none of those you can use as sort of a basis for fire detection, because you've got to sort of put them in. Or you've got to point your lasers at them, and pointing lasers at things other than in sort of lab conditions is not really appropriate. People have done some CFD of this using large eddy simulation, and done quite well at predicting the frequency. When it comes to fire detection, the only real approach that's been used where flicker is the mechanism is video analysis. It's not used in industry, it's just a research tool at the moment. I mean, it's a fairly complex business, and also what you've got here is a bit of technology that is almost as expensive, maybe, as the flame detectors that they might replace. Well, I'm not saying it's expensive as that, but it's not cheap. It's not cheap. Okay. It's certainly not been taken on by industry now. Okay, so the basic idea that I'm running with is I've got a thermocouple, I've got external to the fire. The nirvana is measuring the instantaneous radiation, which I'm not going to be able to do. Okay, but to get some handle on that radiation field is the idea. And it's a similar sort of problem to the measuring the velocities. I've got to log quickly. I've got to have low thermal inertia. Log quickly, low thermal inertia. The only thing that I haven't got to worry about is I've got 2 thermocouples. I've only got 1 thermocouple. And of course, the signal I might get out might not be really very easy to analyse. Okay. So let's have a look at this. So I'm working with our 4th year students on our BEng degree. So we start fairly simply. So what I've got here is a radiant burner. It's a really nice burner because it does this. To heat the room up nicely. It's not a technical piece of instrumentation. And it does it really quite slowly, period of about 8 seconds. And then what we've got is we've got a sensor to a very cheap logger. I can log at about ½ a second a measurement with that thing. That's no good later on because I need to log quickly with a fire to my laptop, the student's laptop. And this is the sort of thing that you get out of it. Warms up, and these oscillations you see are the oscillations of the fire, so we're certainly capturing that. It's difficult to see here, but what you've also got is you've got sort of a large scale, or a sort of a low amplitude, large period, that's what I'm trying to say, a large period oscillation in there. And it is there always, whenever we do these measurements with this sensor, we always get that. We believe, I'm fairly sure it's true, that it's to do with the fact of where we're doing the measurements. We're doing our workshops, great big space, and it's sort of like a characteristic of the air movement in there. Okay. Which is a shame, because I wanted something that would be very simple, and it got slightly more complicated. I mean, you can model that in by modelling the heat transfer coefficient or adjusting it. We haven't done that here. What I'm going to show you, but in other analysis we have. What we do is we throw away the first bit, principally because we find that the thermal inertia is really of the thermocouple is affected by the polystyrene. It takes a bit of time for the polystyrene to warm up. And so you cannot use the same time constant tool here as you do here if you take the whole set of data. Okay. So we changed the model a little bit. I thought it wasn't going to change quite as much as this, but there are reasons why it's changed as much as this. I could talk about after if you really want to. But essentially we've got quite a few constants in here. We've got the mean heat flux, and then we've got the amplitude of these two sine functions. We've got the frequency, which is actually what we're trying to get from all this. And we've got the two phases. So it's about 8 parameters. Of those 8, we only really want the frequency. And what we do is similar to the heat flux, in that we curve fit this to the measurements by optimizing the error, minimizing the error. You know, it's not one parameter, so we've got to use something a little bit more clever than we were using before. We use the simplex method because that doesn't require a derivative to optimize, and I haven't got a derivative, so that's good. Sometimes it's called the amoeba method because the simplex looks like an amoeba as it's moving across the space. Sometimes it's called the bikini method. Google the bikini method, you'll find out all about this technique. That's a joke, by the way. Anyway, so we do the optimization. And doesn't look great, but it's a reasonable fit. Importantly, we can predict the period really quite accurately. One reason why it's not great is because of this variation in the heat transfer coefficient, small variation in heat transfer coefficient. If you look at the range of temperatures we've got here, we're going from about 324.5 to about 326, about 1.5 degrees. Okay, that's not a lot of signal difference. So, if you take a Fourier transform of the prediction, I beg your pardon, measurements, what you actually find is that the Fourier transform doesn't pick up on the 8-second period that is measured by, very simply. Why? I don't know. I've talked to somebody who I believe and trust who does a lot of signal processing, and what they have said to me is, well, it's a low frequency oscillation. You need a lot of data to capture low frequency oscillations. I don't know if I believe that or not, but anyway, that's what I've been told. We've got 7 seconds, we've got 10 seconds, and if you get a 10-second period, you're going to get a 20-second period. Okay. Having said that, why is there not a 14-second period? could ask me. I do. Okay. But it's there or thereabouts. I mean, at the end of the day, it would be great if I had an 8-second period, but 10 seconds, 7 seconds, it tells me, I'm close enough in engineering terms, I would say. Okay, but that temperature variation just wasn't really enough. If you're applying that to a real fire, the chances of success are very, very small, in my opinion. So we developed a better sensor. We've got this little parabolic dish. You can actually buy these off the shelf. They're used for solar, starting fires. Well, fires that you want to start in the open from the sun. Okay, so you can imagine that this is amplifying the signal. And now, rather than heating up a piece of tin foil, a piece of polystyrene, what we're heating up now is the bead of the thermocouple, if you can tune it to get it at the focal point. It's not as easy to do, I'm afraid, as I'd like it to do, particularly if you use a really small bead. But that's sort of where we've taken it. Now the model has changed because we've got this parabolic dish. With this approach, you sort of have to guess how the incident heat flux varies. With the flat surface, the Mark II model as I called it, you have Lambert's cosine law that's telling you that the variation as you change the angle of the heat to the surface is going to go like the cosine. Cosine sign doesn't really matter. So you've got some theory there that gives you a helping hand about what the instant heat flux is going to look like. Here, you haven't got a lot of helping hand, I would say. You've got this parabolic dish, it's going to modify the instant heat flux. Rather than start off with the mean heat flux, we start off with the background radiation. So the logic being that if my fire's over there and my sensor looks like that, then all it's going to see is background radiation, sigma Tm to the 4. And then, rather than sines and causes, or rather sines, I beg your pardon, by a little bit of experimentation, we really came up with, well, we have to, for a start, first of all, we have to have the absolutes in there because we can't have an instant heat flux going below the background radiation. And then we put these powers on here to try and get a better fit to the experimental data. And you get a very good fit. Strangely, first of all, the temperature range is much bigger, which is going to be good for signal to noise ratio, but the predicted is not as good as it's not as good as the old way of doing it, really. Again, why, I don't know. I'm going to have to repeat this when I go home, because I don't understand why we get this error when our curve fit is so good. That if we take a Fourier transform, again, we're seeing the same peaks. It's the same fire, so I would expect to see the same peaks. I don't know why I've got this one in here, that's just 10 seconds. But again, there's the 8-second period that I should be getting in the model if it was a good model. Okay, so that was sort of like, we're not playing around because the student takes it all very, very seriously, but the ultimate is a fire. If we can't deal with a messy signal, then we're wasting our time. Okay, so what we've got here is the temperature signal taken from a pool fire with that diameter. It's a round pool fire. It's sort of heptane. It's not quite heptane, but think of it as heptane. And we're logging at 100 Hertz, which is absolutely fab because we're looking for something about 3 to 4 Hertz. So we're logging quickly enough. The question is whether the thermocouple is sensitive enough. Now, I can't, at the moment, I haven't attempted to apply the lump capacitance model to this. I suspect it would fail miserably. Okay. Possibly we could pick 20 or 30 seconds of data it would make some sense in and give that a go there. Maybe I'll try that. But what we can do is we can take a Fourier transform of it again. Now, initially I looked at this and I thought, oh dear, this is not good. We've got the 50 Hertz, we picked up on the 50 Hertz anomaly to do with the AC supply. And what I really wanted was, what if I had that, somewhere between 3 and 4, I don't know, maybe I'd buy the department a few bottles of champagne or something. Because I haven't got these facilities at home, I can't run pool fires at home, they're too dangerous. But there is something there. I don't know if it's significant or not. This is sort of half-baked at the moment, it's not complete, it's not the final answer. If I go down to 1 to 20 Hertz, then I have this line on here because there's a correlation that I haven't measured the flame flicker because that involves getting the video out and doing a frame-by-frame analysis of it, which I might ask a student to do, actually, because I don't want to do it. But I have a correlation, and I don't know how accurate the correlation is, I'm going to have to dig a little bit more deeper into that says I should expect a frequency of about 3.2 Hertz. Okay? Now, if I focus in a little bit more, then that looks like a big distance. It's actually only 10%. All of what you're seeing here is sort of low frequency noise. And so I'm quite excited by that, because I haven't been able to focus this thing. All I can do is to try different locations for my thermocouple. When I focus it at home, I think we'll get a better result. Or if I take a portion of this data, I'll get a better result. But I think that is, I've sort of achieved what I set out to do. I mean, if that was a thermodynamic correlation, if it was within 25%, I would say, okay, well that's probably good enough. But I think we've measured the frequency of the flame. But I want to take it home and show it to the people who know a bit more about signal processing than I do, and see if they get excited by it or not. Well, they won't get as excited as I will, but that's really all I wanted to say. I mean, so far, so the heat flux measurement, that works really well. We've taken the velocity measurement too. Yeah, it probably does the job. We're not going to take it any further than that. And the third one is clearly a lot more to do with the flame flicker. Because I haven't got real fires, I've got a student at home working on what we call the paddle rig, where essentially we'll be able to figure out how high we can push the frequency of the flicker, and the thermocouple will be able to detect it. Obviously we want 20 Hertz, but whether we'll get that or not, I don't know. Imagine we've got the sensor here, and we've got the burner here, or radiant burner here. I can put 3 modes into that, because I can put speed controls on these things. So I can change the rate that these things rotate at, and I can have my burner doing a bit of that as I want to as well. Well, I've also got some ideas, and I picked this up while I've been here actually talking to people. I think we can build a little fire where we can control the flicker in a similar sort of way to with a speed controller. And I've fallen in love with FDS just like everybody else, so I'll get a student looking at seeing if they can produce a pulsating flame as well. But this is happening now. The students actually working. We talk to each other every day. That will be next year. Okay, that is all I really had to say. I haven't put a slide on here that says questions. I've put a slide on here saying acknowledgements. These are the students. 2 of them are out there earning a living now. Tiger Donovan, he's a fellow lecturer just like me. But the 2 are out there earning a living now. They're probably earning more than we are. So I will stop there. If you have any questions.
We have time for a few questions.
Yeah, I've got lots of questions actually. I'll get started.